Hello and welcome everyone to the presentation of the modular optimization framework for mixed, expensive and inexpensive real-world problems. This is a joint effort between CJOB Naval Architects and the Network Computing Group from the Leiden Institute of Advanced Computer Science. My name is Roy de Winter and I worked on this together with my promoters Thomas Beck and Nicky van Stein. Let's go straight to the problem statement, what we are trying to solve today. The problem of today is two real-world problems that we are optimizing. We are optimizing two ship design problems. First problem that we encounter is the bulb of an existing ship. We have to refit the bulb to make it more efficient at lower speeds. The second problem that we are optimizing today is the hull below the waterline of a ferry that is to be built to be able to sail on batteries between the Greek mainland and a few islands. A formal problem statement is defined as follows. Here f is the objective function, g is one of the m constraint functions, and there are d decision variables. The objective functions f and the constraint functions g can be either computationally cheap or computationally expensive. Usually, those problems are optimized with Bayesian optimization algorithms. However, what to do with computationally cheap constraints, and what to do if the objective is cheap and one of the constraints is expensive? I found a solution for that. And the solution for that is the Magov optimization framework. Magov stands for Modular Adaptive Global Optimization Framework. This is basically an efficient global optimization framework with different modular components, like the infill criteria, the design of experiment size and strategy, and finally a setting that define how expensive or inexpensive the objectives and constraints are. For every level of expensiveness, there are three, there is a different strategy for evaluation. For the most expensive one, a set of radial basis functions are as surrogates are fitted, and for the most inexpensive functions, they are directly integrated into the acquisition function, where searching for promising solutions is done on the surrogate. Then finally, for the most expensive levels of functions, there is a separate evaluation strategy. This evaluation strategy is defined as follows. There's three levels of expensiveness. The computationally cheap functions are directly used when optimizing the acquisition function. Then there can be computationally inexpensive constraints that are not really expensive, but also more expensive than fitting and interpolating a surrogate. For this level 2 of expensiveness, also surrogates are used, and they will be evaluated before a level 3 expensiveness level function is computed. The level 3 expensiveness is therefore only evaluated if all the constraints of level 1 and level 2 are satisfied. This way, no invalid solutions are evaluated, and the surrogates for level 2 expensiveness functions are updated after each evaluation, and the most inexpensive functions can be evaluated indefinitely many times when searching for promising solutions. So I tested this Magov framework on a set of benchmark functions. The benchmark functions selected are the G test functions. There is 4 experiments done. The traditional way, where every function is considered expensive, so classic Bayesian optimization with constraints. The constraints first way, only evaluate the objectives when the constraints are satisfied and update the constraint surrogates after every iteration and only the constraint functions when they are infeasible. And the objective is only evaluated when the constraints are feasible. In the constraints integrated way, the constraints are directly used in the optimization algorithm so that the acquisition function can be optimized while being sure that the constraints are feasible. So the constraints are directly used instead of a constraint surrogate. And finally, an experiment is done with a generalized expected improvement acquisition function that can propose multiple solutions per iteration. For our problem, our benchmark test, we selected 3 solutions per iteration. To no surprise, the constraint integrated approach usually finds the best solutions in the least amount of evaluations. So let's now go to the results of the real-world problems. The first case is a refit of a bulb of this container vessel. This container vessel has a capacity of approximately 10,000 containers. This vessel had a design speed of 26 knots, while it should sail between 13 and 20 knots. There's 4 conditions with different rods. This was done to save fuel and to emit less greenhouse gases. The only change that was allowed of this vessel is a bulb, or how we call it, a nose job. Because there are 4 important conditions, the vessel will be sailing in a weighted. Because there are 4 important conditions the vessel will be sailing in, a weighted single objective function is created to minimize the power required to sail in those 4 conditions. Due to that we had to optimize for these 4 conditions, it is difficult for a naval architect to design one bulb that performs good in all these conditions together, given that the weights are very diverse. So here is the CFD setup that we use to evaluate the performance or calculate the power that is required to sail at the design speeds. As you can see around the bulb, the grid is very much refined, while further away, further away, the grid is more coarse. Since it is a symmetric ship, we only evaluate half. This results between 1.7 and 3.7 million cells. One evaluation required 20 minutes on a cluster with 120 cores. Because there's 4 conditions that we have to evaluate, one evaluation of those 4 conditions required 1 hour and 20 minutes. Well, the constraints were very practical and could be calculated instantly and were therefore directly implemented into the optimization algorithm. Here you can see the optimization result. This is the convergence plot where the evaluation of the 36th evaluation, the 26th evaluation and the 27th evaluation, my colleague wanted to try a few evaluations himself that he thought would be good. As you can see, the results, this resulted in very very bad results. Since it was so difficult for him to actually think of what would be good for these 4 different conditions. In the end, a 5% reduction of power was achieved by changing the bulb in the 43rd iteration. So here you can see the original bulb and the wave that it generates at one of the speeds. And here you can see the new bulb. And as you can see, there's quite a bit of differences between the two, as the original bulb makes much larger waves compared to the optimized bulb. And therefore, this new optimized bulb requires less energy. Okay, let's go to optimization problem 2. In the second real-world problem, we optimize the hull for this roll-on, roll-off vessel. On this ferry, the cars roll on the back and roll off in the front. We optimize the hull below the waterline. This vessel only needed to be optimized for 1 speed, and therefore 1 evaluation required 20 minutes on the cluster. The constraints, on the other hand, are hydrodynamic constraints and needed to be calculated in a specific software. The volume of one of the constraints is, for example, the volume of the hull. The volume of the hull should remain approximately the same, 1% percent error margin was allowed, and the center of gravity should also remain the same. Those constraints can be calculated instantly on a laptop. However, as I said, it should be calculated in a specific software, and there was some communication time between the algorithm and the software. So those constraints could not directly be integrated into the algorithm, but a surrogate is also used for those constraints. However, first we made sure that the constraints were satisfied before the computationally expensive objective is evaluated. Two independent experiments are conducted in the study. One experiment is done with naval architects and hydrodynamic engineers, and the other one is done with the optimization algorithm. There was no communication between the two teams. So here's the original hull. As you can see, there is no bulb yet. And this is the result of the hydrodynamic experts and naval architects. They used a knuckle line below the bow and integrated the bulb there. This resulted in a required in a 20% reduction of resistance. This required approximately 2 weeks of work by the naval architects. And then here is the result from my optimization attempt. As you can see, the algorithm really started learning after the 8th iteration, which was no surprise as there were 7 independent parameters on the design of experiment of 8. After the 8th iteration, the algorithm converged quickly to the better solutions. Also, a 26% improvement was found. However, remember that this was a roll-on roll-off ferry, and this result has a pretty large bulb sticking out of the front of the vessel. The design would therefore require quite a large ramp for cars to roll off from. The client therefore opted for the expert's choice instead of this hole. This highlights that optimization is not actually that difficult, but it is setting up the parameterization and parameterizing the problem. So my conclusion for today is your algorithm can only find as good solutions as your parameters allow, and a lot of effort is required in setting up this parameterization. Then it's obviously important to choose your objectives and constraints wisely and exploit the inexpensive functions where possible. Thank you for listening. If you have questions, please reach out via email or via Wahova.